Um, Yesterday I did polar area, and I feel like there are certain things I could have done a little bit better, so I'm going to try to do a little better job. Not try, I am going to do a better job today, just kind of explaining some things with this one problem that I shared with you, and we're just going to do this problem, and then basically you'll have the rest of the period to work on getting ready for your test on Thursday, asking me questions and all that. But yeah, I just think there's some things I need to make a little bit more clear and do a little bit better job than what I did yesterday. So like, big idea that I hope you did at least pick up on from yesterday is that when you are doing polar area, the formula we're using is based off of a sector area. And it's the integral from a starting angle to an ending angle of 1/2 r squared d theta. And that's definitely the formula that you want to know. And the main thing that I think I wanted to first emphasize and do a little bit better job of explaining what we're doing is that when we are doing area in rectangular mode, we're always kind of either moving just up and down or left to right. If we're doing area in polar form, everything is always going to the pole because all of these functions we do are always kind of centered around the pole. What's changing is that r. So if I'm looking at this region, the way I kind of think about it is if I start drawing in all these radii through the region, that can inform me how many integrals I need to use. So again, I'm going to always draw these coming out from the origin. So I start off as I come out from the origin, kind of connecting the graph. There's all my radii. I'm kind of hitting that circle. Once I get to that point, as I start coming out, I'm going to switch this to, we'll do it in orange. I'm hitting another graph. You can kind of see here's my r values, it goes around, keeps going around. And then I hit this point, and it's going to switch over to the other graph again and fan out to fill out the area. So you have to imagine that when we're filling out this area defined, we're basically kind of drawing like, I don't know, this like sunburst coming out from the origin to kind of fill in the shape. So if we're looking at this graph right now, it would be 3 integrals I would just set up. Again, one thing that we can rely on and one thing that is going to be very helpful to you is that we just ignore a portion of the graph. It's like I'm just going to pick to leave off that left-hand side. I can just double my integral to find the area of the entire piece. And so setting up this problem and some things that I wanted to kind of be a little bit more clear about. So we are going to need to use 2 integrals. I'm basically going to have the integral for that tiny blue sliver where I'm touching the function r. And then I'm also going to have the function, the much wider part where I'm actually touching the function s, which is what I have kind of outlined in yellow. So setting up this integral and setting up this problem, my basic idea is I know it's going to be 2 integrals added together because we kind of have 2 pieces going on here. And I am doubling this to basically include that entire region. So there's kind of like the bare bones setup that I'm using. So using this kind of idea in this graph, I might first say, hey, I need to figure out where those integrals are going to flip out. I want to figure out, hey, what is the theta when this region is switching over from one graph to the other graph? Well, how can I find that theta? That theta is going to occur when one graph intersects the other graph. Setting them equal to each other, we get 4 sine of theta is equal to 2, sine of theta is equal to 1/2. So theta is equal to, we have like pi over 6, we have 5 pi over 6. But to be clear, like all the coterminal ones that come after that. So by solving that, we're kind of thinking like, hey, pi over 6 is one of my answers. It looks like this angle right here is pi over 6. And then whether I write it down or kind of think about it, like this is the blue region touching graph r. So what is the r when theta is pi over 6? Like clearly we know what it is, we solved it. the sine of pi over 6 is 1/2. We get 3/2. We have like that positive r. And again, that's just like a good thing to check because we know when we use this problem, we either want it to be all non-negative or non-positive. If you skip that red part for most problems, you would probably honestly end up being okay. But I can see that this blue portion is ending at pi over 6. And so I have like the 1/2. It's touching r. So there's my r squared d theta. And then what I don't think I did a good job yesterday doing, and what I wanted to kind of fix, is we want to figure out where this area is starting at. And what I did yesterday, I was like, hey, it starts right here. Let's just pick a theta and guess what that theta was. And what I wasn't clear when I said this is, I personally was like looking at the graph, and I knew what that r value was, and I just kind of picked what I thought made sense to be a theta to make that value work. And what I mean by that, this area is starting right here on the origin. Well, if I am on the origin, what does r have to be equal to? R has to be equal to 0. So I basically want to find the theta when r is equal to 0. Well, what is r? It's touching that graph of r, 3 sine of theta. So basically I am solving this equation. What I didn't really say very well yesterday is I was just kind of guessing a value because I don't need to solve it because I know I can look at that equation and know automatically that pi over 2 is going to be something that works. Or not pi over 2, clearly I can't do math. When is sine equal to 0? Sine is equal to 0 at 0, and that's the one that kind of makes sense to work. So again, if I'm checking it, I might just say like, hey, let's try the angle of 0, plug it in, you'll see it work. But again, really what I'm doing is I want r to be 0, find the angle that makes that true. So before I kind of finish this problem, say instead I wanted to do maybe the region of the top of the graph, I'm gonna put like a purple dot there, and I said, hey, I want to find the angle where that's happening at. Well, that would be me saying finding when r is equal to 3, and just set it equal to 3, and then solve. Do I often take the time to do that? No, I can pretty easily look at that and see, hey, sine needs to be equal to 1. I know that's going to be at pi over 2. Visually, that's kind of where pi over 2 would be anyway. So like, yes, there is some solving involved, but there's also like, you just have the feeling, you know how angles work and kind of how the trig works and all of that. Yes, sir.
Just to clarify, when you say that's where pi over 2 should be, we're thinking about it like a polar?
Yeah, so pi over 2 would be somewhere along the y-axis.
Okay.
So I knew it had to be something like pi over 2, 3 pi over 2. But when I look at that, I'm like, hey, the equation's 3 sine of theta. What would make that go up by 3? Pi over 2 would have to be what gets plugged in for theta.
Okay.
So there is like, I said guessing, I probably should have been more, find a better word for that. Like, what I don't want you to have to do is like solve a bunch of equations each time when you can kind of like visually look and just figure out if something kind of works out. So finishing up this problem, like the next part is we want to do kind of that orange region. It looks like it should kind of start at pi over 6, like that's kind of where we ended it at. And it's going to be this region touching this part of the graph. Like you could plug it in real fast. The sine of pi over 6, like positive, makes sense. So we're going to say this one is starting at pi over 6. I'm going to have the 1/2 r squared d theta. We do still want to figure out where it is stopping at. And again, kind of similar thing of what I'm thinking. It's stopping at right here, kind of that big black dot, if I am thinking about where it's stopping at. Logically, to me at least, I look at that, I'm like, oh, that's probably pi over 2. Or another way to think about that, what's the r value where I put that black dot? 1. So I'm basically thinking, well, this is when r is equal to 1. Let's think about when this graph is equal to 1. This graph is equal to 1 when sine is equal to 1. Oh yes, I made a good guess. That is at pi over 2. So like if you want to solve a bunch of equations, you can. But again, visually, I think you can look at this and be like, oh, pi over 6 coming after pi over 2. Pi over 2 coming after pi over 6 makes sense as kind of a stopping point. And of course, I'm doubling that. I want to find the entire area and not just half of it. So I hope that makes some things a little bit more clear because I do feel like I didn't do the best job yesterday. But any questions on
the AP exam, you have to solve for pi over 2 if you just wrote pi over 2, because it's like obviously on the axis.
That's fine, that's normally what I would do as well.
Okay.
Like, I might just like mentally, like just plug pi over 2 in to the
Yeah.
function, because there are some weird ones where this point up at the top could be 3 pi over 2 with negative r, but, like, again, typically it should be something logical, and we want the angles to be close together, so like,
Yeah.
it honestly wouldn't make sense even potentially to be 3 pi over 2,
Yeah.
just because of the way the graphs work. So again, for a lot of these, like, not that it's easy, but also like just don't overthink it. Like, just go with your gut what the angle should be, and you're probably going to be correct. Alex.
If the function is like sine of 2 theta, wouldn't that alter what the angle is? And then you'd have to check.
Yeah, but that would be a different graph, and so you would still have like that visual. Like I'm not doing this one. If you wanted to try it, and I can check it in class. Like, there's one that has 2 theta. Still can solve it and find and pick the right angles visually from there. Seth, I think you had your hand up. No, maybe.
Will the graphs ever, like if we're doing a graph in the EP exam, will they ever intersect non-whole numbers?
Potentially, and you can use your calculator to find where those cross at. People at home are good.
If you use like 0, pi over 2, pi, and 3 pi over 2, only one of them is gonna be right every time, right? Or can multiple be right?
Like, for the most part, like, technically, like, this is not the only way I could set up this problem. Like, if I added 2 pi to all my angles, then that's going to be the exact same answer. I guess the main thing you want to look at is, like, clearly theta, like, I know this is exactly what you asked, but really, like, when you're solving those equations, like, how can I say this? There's clearly going to be one that works and ones that like don't work. And you will always have the graph as a visual to look at to help you figure that out.
All right.
So I am going to go ahead and ask you, because I think a lot of this is you just need to practice. I did realize I shared the briefcase binder before I made a correction on it. I'm not taking it away, but I do want you to do the briefcase binder because I think they're useful. That's why I assign it. But there's no quiz corrections, of course. I do have the review problems, the unit summary, and I fixed the unit summary, but the quick reference, I forgot to take off something. So arc length is, of course, on the AP exam. Arc length in rectangular form and parametric form is on the AP exam. But arc length in polar form, which I originally thought was something I had to teach, it is not on the AP exam, so you don't need to worry about filling in that box on your quick reference. It's just in the formula, but not on the AP exam, so we're not going to worry about it. But other than that, I am going to go ahead and let y'all get started, continue working on the homework. I will say I think some of you might be behind on the homework, and I'm just going to be honest. When I go to check homework, I'm going to look mainly at the calculus pages. So like I'm going to check homework 2, I'm going to check homework 3, and I'm going to check homework 5. Clearly, I think you should do 1 and 4 because you need to understand those graphs, kind of understand the calculus of it. But I don't need you to be bogged down with homework and not practice the actual calculus, which is what you need to know. So if you are behind on homework, I'm just going to tell you to just focus on 2, 3, and 5 and the briefcase binder. That's going to honestly be the most beneficial in the whole scheme of things. So y'all can go ahead and get started. I am here to answer questions, whether you're here or at home. Tomorrow's going to be about the same, just a workday, testing on Thursday, and then finally getting to review for the AP exam beginning on Friday. So yeah, fun stuff. Anyone at home have any questions you want to ask while I am by the computer?